Welcome to the second part of Chapter 5.7, in which we visualize the solutions that we've just calculated. So our first question is going to be, how many terms do we need to plot to see a reliable solution? So on the left-hand side, we'll start with early times, and that's going to be the most challenging because we know that the temperature changes quite rapidly, especially towards the edges of the rod, so we expect to need more terms at early times. So we'll start with 6 terms, and we see a sinusoidal shape. At 20 terms, there's more extrema in the sinusoid, but it's starting to flatten out about an average value. We go straight up to 100 terms. It's flattening more, but there are still undulations in the curve. And finally, if we push it up to 1,000 terms, it's starting to look like something that's smooth and continuous without a physical extrema in it. So it takes a lot of terms at early times, and you'll find that you can't actually do the computation for tau equal to 0 because it just doesn't work. So that's early times. We need up to 1,000 terms. But at later times, we expect to need many fewer terms. So let's plot the first term. Oops. So with just one term in the series, we get something that looks physically meaningful at later times. And these are not steady state later times because obviously that would be a flat line. So at 3 terms, we get exact overlap. And we'll go right up, just validate this. We'll go to 100 terms and make sure it's still exactly the same profile as for just one term in the series. So that's a shocking difference in the computational power required at early times versus late times. And it's just something that you have to be aware of when you're evaluating the solutions. Okay, so now that we know roughly how to calculate the number of terms we need, let's have a look at the spatial geometry of this problem. And so in this instance, we're going to be evolving in time from early times at the top of the plot to later times, where we're almost at steady state with this last one. And the coordinate here is our non-dimensional spatial coordinate along the length of the rod. We see that it's a symmetric problem, as we expected. And we also see that at early times, the curve is much less smooth, and at later times, it starts to smooth out. It almost looks parabolic, and then it just collapses into a straight line because at equilibrium, the temperature is going to be constant across the entire rod. So that's how the solution evolves in time. And similar to last week, we can actually plot this as a heat map because there's 2 independent parameters, xi and tau, and 1 dependent parameter, theta. So if we plot this as a heat map, it takes a little thinking here, but this is our x coordinate as before, or xi coordinate, and along this axis, we're increasing the time. And then the color that you're seeing indicates the value of temperature. So it's just a heat map, but instead of a spatial 2D map, it's a spatial temporal 2D map. And so what that's showing us is that actually most of the interesting changes in temperature occur at very short times. So if we zoom in on this length scale, we can see a little bit more of the nuances. And it looks like there's lines roving across the figure, but those are actually just pixels because I've chosen a fixed resolution for this plot. I've only chosen the full plot to have 100 rows and 100 columns. So if I were going to redo this calculation, instead of calculating from non-dimensional tau values of 0 to 1, I would just calculate tau from like 0 to 0.25 so that I can focus in on this more interesting region. And then you would see that these become less pixelated as you add more data. So that's what our solution looks like in time. Symmetry enables us to reduce the number of computations if we just calculate half of the problem and then revolve it around the axis. And we see that we can apply the same heat map visualization techniques as we did with the last problem, even though this is a temporal problem. So thank you, and I will see you next week.